All right, so here it is, the bonus question for the properties of logarithms. Now, this I do actually encourage you to try this yourself first. So try yourself first. Now, one thing that you should know before you try yourself is this. We actually have a pretty complicated looking expression here. It's in sigma notation, which we haven't seen since we did sequences and series. And we have the reciprocal of some logarithm of some changing base, right? First it starts at 2, then it starts at 3, then it starts at 4, and subsequent terms. And we also have this input with an exclamation point. And this exclamation point, it doesn't necessarily mean that we're excited about the input and we want to shout 100 or anything like that. It really has a very specific meaning, actually. And it's a meaning that we usually teach in, or we did teach in Precalculus 12 when we taught combinatorics, but here's what it means. Factorial. This is what an exclamation point means. So 100 factorial really just means you take the number in front of the factorial symbol and you multiply it by the next number down in the natural numbers. And then you multiply that by the next number down in the natural numbers. And then you multiply that by the next number down in the natural numbers. And so on and so forth until you get to 2 and then 1. You don't necessarily need to write the 1. It doesn't really change anything, so you could just write 2. That can be where you stop. So this is 100 factorial, and it's actually an enormous number. If you think about it, even if you try rattling off out loud what this operation would entail, it would take you a while to count down from 100, first of all. 100 times 99 times 98 times 97 times 96 times 95 times 94 and so on. So it would take you a while to rattle it out loud. But it's also something that your calculator couldn't even calculate. It's such a huge number. So this is huge. I think your calculator might be able to calculate something like 60 factorial. I don't think it would be able to calculate 70 factorial, though. It's too big of a number. So anyways, that's what factorial means. So please try this yourself first. Pause the video and try this yourself first if you would like, because it really makes watching the rest of the video more rewarding if you try it yourself first. Okay, so here we go. Sigma notation. What this really means is we are just going to take a bunch of terms and add them together. So the first term is going to be log of what base? Well, it says that we're starting at k equals 2, and our input of our logarithm is 100 factorial. And then we're going to add 1 over log base, well, what comes after 2 for our natural numbers? 3. So log base 3 of 100 factorial. Plus 1 over log base, what comes after 3? It looks like 4 is going to be our next base, and so on, right? We can just keep going until we get to our last term, which is log base 100. That's where our sigma notation tells us to stop, of 100 factorial. Now, this looks pretty unruly, pretty awful, actually. First of all, we have a bunch of different logarithms with different bases. So that's one complication. We have this awful input of 100 factorial, this enormous number, and they're all reciprocals, right? So this is really complicated. But if we scroll down, we might be able to see our logarithm rules here. We have something that I've already pointed out. We have a change of base rule. We also have this sort of corollary rule, which is a change of base that involves reciprocating. So if we have 1 over log base b of a, we can just write that as a logarithm without a fractional component, as long as we swap the base and the input. Right? We swap b and a. So previously b was the base, now a is the base. Previously a was the input, now b is the input. So we can apply that rule, that property of logarithms, to this particular expression for every single term, actually. So if we do that for the first term, this sort of corollary change of base rule, we can just write this really ugly term as a nicer looking term, log, without a fractional component. What is our base? Well, remember, we are swapping our input and our base. So our old input of 100 factorial becomes our new base. Our old base of 2 becomes our new input. And we'll do the same for every logarithm, for every fraction here that we see. So again, to write this as a simpler logarithm, just log, we can swap the base and the input. So the old input becomes the new base, the old base becomes the new input, and so on. Do the same thing here. 1 over log base 4 of 100 factorial is just log of 100 factorial, log base 100 factorial, pardon me, of 4. And then we just keep doing that to all of those logarithmic terms, and then we do that to the last term as well. So log base 100 factorial of 100. There we go. So this looks a little bit simpler at least. We don't have all these fractions, but still it looks pretty complicated, right? We have this strange, huge, enormous base for our logarithms, but a key here is that actually every single logarithm has the same base. So what we can do in this case is actually apply the power rule. So not the power rule, pardon me again, the product rule. So all of these logarithms have the same base, and we're taking the sum of all these logarithms. So we can just write that as one logarithm where we take the product of all of their individual inputs. So this is just going to be 2 times 3 times 4 times, and so on, until we get to 100. So this definitely is simpler so far, right? We went from something like 99 terms to just one term, and it doesn't even have a fractional component, but it still has this enormous base and this enormous input. And it's actually something that we should be doing is comparing the base and the input, because if we look at the input, 100 times, you could say times what would be the next number previous to this 100? It would be 99. Oops, 99. And what would be the next number after that? It would be 98, and so on. And until we get to 4, 3, 2, and so on, just 1. So there we go. So this is actually what we have as our input. And if we remember, this is actually what we mean by 100 factorial. So what is another way we can represent our input? We can just say that our input is 100 factorial. Right? It's the same thing. 100 factorial means you take 100 times 99 times 98 times so on and so forth, times 4 times 3 times 2. So this input we can write more simply as 100 factorial because it is 100 factorial. So what can we do with this? Log base 100 factorial of 100 factorial. Well, remember, this logarithm represents an exponent that you would apply to base 100 factorial to get 100 factorial. So you could say 100 factorial raised to what power would equal 100 factorial? Well, to the power 1. So that's our answer. 100 factorial raised to the power 1 would get you 100 factorial. So that's what this logarithm represents. It represents the exponent on base 100 factorial that you would place or apply to get 100 factorial back. So hopefully that's a surprising answer, because to me at least, when I first looked at this, it didn't necessarily, the answer of 1 didn't necessarily jump out at me, but it is actually pretty amazing that out of all of this sort of seeming chaos, you actually get a very, very simple number. So I hope this was fun, but I also hope that this inspires you to look at more fun logarithm questions in in math contests. So the particular math contest I would recommend you try is from Waterloo University. It's a premier university for computing and mathematics in Canada. And the particular contest I have in mind that you should check out is the Euclid contest because they often, I think always, have an interesting logarithm question in them. So if you type this in Google, Waterloo Euclid past contests, they have all of their past contests online. And this might even be of more help. They also have their solutions, really detailed solutions. So if you feel like you're stumped on a particular question, you can start to look at their detailed solutions until you start to approach an understanding of it, and then maybe you can even try finishing the rest of it yourself after you look at some hints in the solutions. So there you go. Hopefully, don't worry, this isn't a question that I would ask on a test or anything, but it is at least a fun question, a math contest style kind of question. And I do encourage you to try exploring different kinds of problem-solving questions like that.